Bernard mentioned several times the importance of optimization, and that's nice because today we have Robert Vanderbei, who's a professor of operations research at Princeton and an expert in optimization.
Thank you.
Over to Robert.
Okay, so I'm just going to give a very basic introduction over the next few hours. Today we'll talk about linear programming, and toward the end of the course on Monday we'll move on to convex and more general nonlinear optimization. Okay, so linear programming, I guess we should start with what is it? So we want to maximize or minimize a linear function subject to constraints. Of course, if we were just maximizing a linear function with no constraints, the problem would be rather simple. Infinity would generally be the answer, or a constant. So we have constraints, and there's different ways one can pose the constraints. I call it standard form if the constraints are posed exactly like this, that you have some inequalities, linear inequalities. So we have this matrix A. I will try to be consistent in my notation later, and A will have m rows and n columns. And so we have AX less than or equal to B, and by less than or equal to, B is an M vector, and by less than or equal to, I mean that each component of the vector on the left is smaller than or equal to the component on the right. And also the vector X I'll take to be non-negative. Now, you may have encountered linear optimization problems already in your work, and they may not have been in this form, but it's very easy to convert from one form to another form, and I like this form, and I call it standard form for reasons that I hope will become very clear as these lectures proceed. So that's the problem. Many, many applications. It's important, of course, broadly and in machine learning applications. So the first thing we want to do is have an algorithm, and the first step to the simplex method is to introduce something which I'll call a dictionary. And so all I'm doing here is I'm introducing a notation for the objective function, and I'm also introducing slack variables that represent how much of this inequality deviates from being an equality. So W is just B minus AX. It's the difference between the right-hand side and the left-hand side. And so because of this inequality, W should be greater than or equal to 0. And I call this a dictionary is because the variables on the right, X, define the variables on the left. And this is, of course, completely trivial right here, but we are going to modify this dictionary on the next slide, and the whole simplex method is based on iteratively modifying how we represent the dictionary. Associated with this dictionary and each of the subsequent ones that we're going to see is what we call a dictionary solution. And that's a particular potential solution to the problem. So it's a candidate for a solution, but we'll just call it a solution. And we'll distinguish it from the final solution, which we'll call the optimal solution. So the dictionary solution you simply get by simply setting the X variables equal to 0 and reading off the W's. Completely trivial in this case, but it will become more interesting as we iterate things. Now, so that's a particular solution associated with this way of writing the equations. And if, and as we do that, of course, then W is just equal to B. And if B is greater than or equal to 0, then W is greater than or equal to 0, and this dictionary would be feasible. It satisfies the constraints of the problem. Might not be optimal, but if B is greater than or equal to 0, it's feasible. If B is greater than or equal to 0, which makes it feasible, and C is less than or equal to 0, then there's no further improvement that you can make, and this dictionary solution would be optimal for the problem. But not very many problems have the property that 0, 0 is the optimal solution. And so we need to iterate generally. And let me see here. Okay, so here's how the simplex method goes. There's two things. There's feasibility and optimality, and I'm going to first discuss getting a feasible solution. Sorry, I'm first going to discuss going from a feasible solution to an optimal solution. So the primal simplex method refers to exactly that. We're feasible and we're working our way toward optimality. And so the B in this picture would be greater than or equal to 0, but the C is not all less than or equal to 0, and so I need to address that fact that the objective function can be improved. So I look at the objective function and say, well, if there's an index j for which the coefficient on that variable xj is positive, then I can improve things by letting that variable increase from 0, which is where it is in my dictionary solution. So I want to let that variable increase from 0, and that we'll call that the entering variable. Maybe I should say right now, the word entering refers to these variables are over here are called basic variables, and you're entering the basis. And these are called non-basic variables. Of course, right now, these are just the original variables, and these are the slacks, but eventually they'll be more intertwined. So, so xj will enter. It will become one of the variables that's not 0. And we want to preserve this property of having a dictionary. So if I take one of the variables on the right and put it over on the left, I need to take one of the variables on the left and put it over on the right in my system of equations here. Just want to rewrite my system of equations with one xj swapped with one of the w's. And so how do we figure out which w has to go? So we've picked this index j, and we're increasing that particular variable xj. All the other ones are equal to 0. And as we increase it, the column of this matrix associated with with variable xj starts to get subtracted off from the vector b. And vector b was greater than or equal to 0 because we're feasible. And eventually, one of the components of w will hit 0. Might happen right away, but eventually, it certainly should happen. And so you look at the first index, I, where as you increase that one variable x, this b minus a times that column of it, b minus that column of the A matrix equals 0. You pick that I. And that's our leaving variable. And now we just do algebraic rearrangement of the equations to put the variable xj on the left and the variable wi on the right. And I will show you how to do this. I'll show some examples in just a few seconds here. But it's trivial algebra. It's just exactly like Gaussian elimination, where you have, it's not an entire Gaussian elimination, where you're zeroing out one column in your process of inverting a matrix using Gaussian elimination. And you'll see what I mean in just a minute. So we get this rearrangement. Now the x's and the w's get kind of mixed up, and they get more and more mixed up as we do this several times. And so in general, the notation will be like this, that I'll have some non-basic variables, which I'll denote by x subscript n. And that's a mix of the original x variables and the original w variables. They get all mixed up. And I'll have basic variables, xb, and that's the rest of the variables that aren't in the xn. And the coefficients that get multiplied here will change, and so I'll put a little tilde up here to indicate that the numbers here are different, because we've done this Gaussian elimination type step, which we call a pivot, by the way. And b and a also get changed, so I put tildes on top of that. But all the variables are still non-negative. And this is a completely equivalent way of writing the problem as this. And that's the whole point. We go from this to this just by algebraic rearranging of the equations, but we could undo that rearrangement and go back from this back to that. So we haven't changed the problem, we've only represented it a different way. We've taken our dictionary and we're defining different variables. We're taking a different set of variables as our given fundamental variables and defining a different set of variables, xb. And we had a 0 there, but as we do these iterations, we get a constant appearing here, and that is the current value of the objective function And that will go up and up because we're maximizing. So we started at 0, and zeta star will go higher and higher as we iterate. So let's see if I'm on the internet. I can actually demo this. But I'm not. But I also have a local version. So I can skip doing that, and I can demo it here. Oops. Let me just make sure it's feasible. The problem, the little tool here doesn't always generate feasible problems. So there's a feasible problem right there. And so in this particular problem, I have two objective coefficients that are positive. I could pick either one of them as the entering variable, either x2 or x4. And we have to make a decision, so I'll pick x2. I picked it because it has the larger coefficient, but there's no guaranteed benefit in that. It's just tempting. So I'm tempted, and I'll pick x2. Now, as I look down the column here, so all these variables are equal to 0 in the dictionary solution associated with this dictionary. And now I'm thinking about improving that solution. So I want x2, which is currently equal to 0, I want it to increase. And as it increases, this W1, which is currently 5, starts to go up at a rate of 2. And so this one's going to go up. And I don't have to worry about this W1 equals 0 ever. And similarly with all the other ones that have a negative number inside this little box here, and they have the negative outside, they're all going up. So W1, W3, W5 I don't have to worry about. But W2 and W4 are going down. W2 starting at 9 and going down at a rate of 2, so I can go 4.5 before that hits 0. W4 is starting at 2 and going down at a rate of 2, so I can only go up to 1. So when x2 equals 1 here, W4 will be equal to 0, and that's the first one to hit 0. So W4 should be my leaving variable if x2 is my entering variable. And I'll do that in just a second, but let's just look over here. I could have chosen this one, but I'm not going to. If I did this one, I would have only these two to look at. So the 4, and is that a 3 there? So we're at 5, we're going down to a rate of 4. That would hit 0 after 1 1/4, after x4 gets up to 1 1/4. This is at 9, we're going down a rate of 3, so x4 could go up to 3 before W2 equals 0. So if I were to pick x4 as my entering variable, then W1 would be my leaving variable. So it's either this one or this one. So I'm going to pick this one. And now the algebra, which I think you can all do it, but let me just describe it without actually doing it. I want to put x2 on the left, so I would just take this equation here, and I would write x2 on the left, so I bring 2x2 to this side, bring W4 to that side, divide through by 2. That rearranges that equation. But then I have to eliminate x2 from all these equations up here by doing Gaussian elimination type steps here. For example, to get rid of x2 in this row here, I have a +2 here and I have a -2 here. So if I took this row and added W4 to it, so W1 plus W4, and I just add all these things, it would be 5 plus 2 is 7, -3 plus 4 is 1. This goes to 0 now, which is good. I wanted to get rid of x2 in this equation. But of course I have a plus W4 when I added it, so I'll subtract that W4 and put that in this slot. And similarly, I go across here and I update all these coefficients. So it's a very simple update of just taking this coefficient, I might get the sign wrong, but something like this coefficient gets updated by taking this times this divided by that and subtracting. Something very simple like that. But anyway, because arithmetic isn't very fun, I made this little Java applet that does it all for me. So when I click this button, it does that arithmetic. I believe that's the 7 and that's the -1 that I mentioned. And when I added the 4, I now subtract it over, and there's the minus W4 appearing there, and I divide it by the 2, and that's why we see the 1/2. Anyway, the pivot tool does all the arithmetic correctly. The objective function was 0 to start with, and now it's 2. It's going up. We're trying to maximize. And, but we're not optimal yet, because this new dictionary, the solution associated with it is not optimal, because x4 has a positive coefficient, and if I increase x4 from 0, I can make further improvement in the objective function. So that's what I want to do next. So I do the same thing that I just did. I look through here. I have to only look at the ones that are going down. So there's a -3, a -4, and these don't have to worry about. So 7 going down at a rate of 3, 7 going down at a rate of 4. That's the one that will hit 0 first. So W2 is my leading variable, if x4 is my entering variable. And so I just click on this little button here, and it does the pivot, and I'm done. And you can always check if you're right. Oh, my volume was too low. There we go. So the buttons at the bottom are just for making assertions. If you make an incorrect assertion, like if I were to say this was infeasible, I get Bart Simpson. You know Bart Simpson? Calling me a loser. Okay. Somebody else is playing. Or is it me? All right. So that is the simplex method. Now, there are some issues that we have to discuss. Wait, there you go. Yes. There are some issues we have to discuss. Some problems are unbounded. The answer is infinity. And how do you detect that with the simplex method? Here's an example that illustrates what can go wrong. So here's this is a dictionary, and we could pick either x1 to be the entering variable or x3. And if we pick x3, we could do a pivot here. There'd be no problem. I'd have to look at the 2, the 3, and the 4 and figure out which would be the leading variable. I do a pivot, fine. But I'm greedy. I go with the one with the largest coefficient, so I pick x1 to be my entering variable. And here, in this case, being greedy really pays off, because if I look down this column here, W1 is going up at a rate of 5, W2 is going up at a rate of 0, W3 is not changing, W4 is going up, W5 is going up. There's nothing blocking x1 from going all the way to infinity. And so the problem is unbounded. And that's how the simplex method detects unboundedness. Okay, so that's one thing that can go wrong, and that's why there's that little button on the pivot tool thing to check. Now, I'm going to show you 3 different algorithms for the simplex method over the next couple hours. And this, I want to show you the first one. So I haven't showed you the complete thing, because what I showed you, I assumed that were feasible to start with. And I only went from being feasible to being optimal. And that's really only half of what we have to do. We have to find a feasible solution to start with. And so that's called initialization. How do we get started with that first feasible solution? So here's a problem where I have some negative values on the right-hand side. And what am I going to do about that? And so these 3 methods that I'm going to show you today are various ways of addressing the initialization problem. I want to start out with the one I'm going to show you now, because it's the simplest. Quick and easy to explain, but as we move along, I'll show you ones that I think are better. But this is a very simple thing to do. Modify this problem just temporarily by subtracting a new variable, which I'll call x0, from each of the constraints. So I'll put a minus x0 on each of these constraints. And for the moment, for the phase 1 problem, change the objective function. Forget about this, because for phase 1, I don't care what the objective is. I only want to get something that satisfies these constraints. And once I get that, I'll reinstate the objective function and start what we'll call phase 2, which is the algorithm I just showed you, the primal simplex method. So we put the x naught on, and so here it is. Got x naught in here. Okay, so this is feasible. Why is it feasible? I can let x naught be a large number, and x1 and x2 I could let equal 0, and I will satisfy these inequalities. So it's a feasible problem, but that's not a dictionary solution. That's just the assertion that there are solutions to this problem. So I would like to solve this problem using the simplex method, and if I get to the point where the objective function is equal to 0, then that means that the original problem was feasible, because x naught was how I changed the original problem. And so if I can make the change of the original problem equal to 0, then I've got a feasible solution to the original problem. So the final dictionary, or the final basis, if you like, the basic variables versus the non-basic variables, the final basis that you get from in this phase 1 problem can then be used as the initial starting point for phase 2. You just throw away the x0, put the correct objective function back in, and continue. If the optimal objective function to this phase 1 problem is strictly less than 0, that means we tried to maximize minus x0, and we, in the end, didn't get to x equal to 0, x0 equal to 0. We got to x0 equal to something positive, so the minus x0 is negative, and that means that there is no solution to the original problem. That means the original problem is infeasible. And so, so here's how that goes. So we can show the problem with x0 in here. So, and the applet that I developed for this two-phase method shows both the original objective function and the phase 1 objective function right below it. And we do pivots, and for phase 1, even though it shows the original objective function, we ignore it. And we just look at the phase 1 objective function with the x minus x0. We do our pivots with this one and with the right-hand sides here. But the first pivot's different, because this is not feasible. Even for the phase 1 problem, this is not feasible because we've got these negative signs here. So the first pivot in this algorithm is special. The first pivot is x0 will enter, and the most negative one will leave. That's just that one pivot you do that. And when you do that, it automatically gets all of these things to be greater than or equal to 0. And now we have a dictionary solution that's feasible. And for the phase 1 problem. And so now we go and we put in, we use the second row to do the phase 1 problem. And so we pick the 4 as our entering variable, so that's x1 enters. We go down here and look at all these things, going from 8 going down at rate 4, from 6 going down at rate 2, from 18 going down at a rate of 7. Turns out W5 is the one that hits 0 first, so W5 must be the leading variable. So we do that pivot. And there it is, and then we have x2 still has a positive coefficient on our fake objective here. And by the way, our fake objective function's value at the dictionary solution is -2. We're trying to push this up to 0. So the 3 on x2 is positive, so it enters. We look through here, 2 going down a rate of 3, 3 going down a rate of 2.5, 7.5, blah, blah, blah. x0 is the one that hits 0 first when I do all those little ratios. And so I have x2 enters and x0 leaves. And I'm done with phase 1. And so the tool here then zeroes out x0 and zeroes out this fake row to tell you that you've finished phase 1, you're done with that. Now it's time for, now you've got to initial feasible solution for the primal simplex method. And so now we go back to the original objective function, and it's not optimal because of the 11/6 here. We go down here and figure out which of the variables must leave. Which one is it? I don't remember. It's, well, we could figure it out easily enough. That's can go up 4. That can go up 5.5. That can go whatever. W4 is the one that hits 0 first. And so we pivot with W4 as the leaving variable, W5 as the entering variable, and we get to a dictionary that looks like this. Their objective coefficients are all negative. The right-hand sides are all positive. This is a completely equivalent representation to the original problem, but when we represent it this way and read off the values that we get by setting the non-basic variables equal to 0, so setting W1 and W4 equal to 0 and reading off the basic variables, x2 is equal to 6/7, W2 is equal to 8/7, W3 is 25/7, W5 is 4/7, and x1 is 11/7. That is the optimal solution to the original problem. So, am I still disconnected from the internet? Yes, how unfortunate. Does this work?
Yeah.
Ah, okay. Wait a minute. Is it really?
Maybe try again. It should work. Just wait for a while. It's really slow.
Okay, well, I have it. Oh, here we go. Java. Java. Maybe it's still better just to. Oh, if I close this guy, close this guy. Yeah. So here we go. We can practice this thing till we really feel like we get it. So the first pivot is special. So for the first pivot, x0 enters, and the most negative one leaves, so that's W5, so I click there. Now I've got all these 1s and 2s here. I don't know, let's pick this 2 here. So x3 will enter. I only have to look at the 4 and the 2 here, and so the 4 going on 13, that's the one that's going to hit 0 first, so I click on that one. Now I have the 3.5 and the 1.5. I pick the 3.5 because it's larger. And I look down here, that's 10.25 going at a rate of 3/4, 15 going at a rate of 5, or 4 going at a rate of 3. This one here is the one that wins. So x0 must leave and x2 must enter. So I click on that. And there I am done with phase 1 in just 2 pivots. All these fractions are ugly, so I'll switch to, all those decimals are ugly, so switch to fraction mode might be more pretty. So I guess we have 207/14 here. So I'll pick that as my entering variable. And I don't know, all of these have the sign that I have to look at all these ratios. They all have, well, they don't have all 14s in the denominator. Most of them have 14 in the denominator, so I can ignore the 14. I can ignore those 7s in the denominators over here. So this is 65 going at a rate of 41, 97 going at a rate of 11, 104 going at a rate of 88. That sounds like the winner to me. 34 going at a rate of 11, 9 going at a rate of 6. I think it was X4. I think it was W3 was the first one. Let's see if I'm right. I got it. Let me do it wrong for the second. If you pick the wrong one, let's say this one seemed like a close contender. You could, the little tool here allows me to do the pivot, because it's just doing the algebra for me, or I should say the arithmetic. It's rearranging things, but if you pick the wrong one, then the one that was supposed to have been picked becomes infeasible, as might others if you picked a really wrong one. So it becomes obvious immediately when you pick a wrong one. And so that was the right one. And so you can have fun with this and just go fast. Oh, see, I got lucky. I could go fast starting down here and click that, and no, that didn't work. I can click this one, that didn't work. Click this one, oh, that didn't work. Click that one, oops, that didn't work. And then click that one. So anyway, okay. So that's the simplex method. Any questions on it? So there's some more subtleties. Any ideas what might be subtle here? What might go wrong? Well, that's what I want to talk about next. What can go wrong? We're doing this because we want to make progress. But it can happen that we don't make progress. Here's an example. So if the dictionary has a 0 on one of these, what I call the right-hand side values, because these are originally the right-hand sides, if one of these values is 0, then this is called a degenerate dictionary. Where's the word? Dictionary is degenerate. Oh, I highlighted the wrong thing here. The dictionary is degenerate if one or more of these entries is 0. Being degenerate in itself is not a bad thing, but doing a degenerate pivot is a bad thing, and that's different. So let's take a look at this for a second. I have all three of the objective function coefficients are positive. I could pick any of them as my entering variable. I am always greedy and choose the largest coefficient, so if I choose the 5 here and look down, this is going at a rate of 2, starting from 1, so x2 could go to a half. This one's going up, so I don't care. This is going down, so I do care, but it's starting at 0. See, so that's kind of a bad thing. I want x2 to increase. I'm trying to increase my objective function 6 to something larger, and nothing changes if I do this pivot with w5 and x2. I can do the pivot. I can rearrange the equations and put x2 here and w5 here, but the objective function won't change. Now that's a degenerate pivot. Not all pivots are degenerate. If I picked w1 for my entering variable, look down here, I go -3, that gives me something there. I got this minus here, so that goes, but this one, there's a plus sign here on the w5 row. w5 goes up, so I don't have to worry about the 0 here when I'm doing w1 as my entering variable. So this would be a degenerate dictionary, but if I pick w1 to enter, it will be a non-degenerate pivot. I will actually make progress. Whereas if I pick x2 to enter, I'll do a degenerate pivot. I'll make no progress. And making no progress is a bad thing. Because it raises the possibility that things can really go wrong. You could make a pivot and make another pivot, and come back to where you started. That would be a bad thing. So that's called cycling. And of course, when we do this by hand on the screen with my little pivot tool, we can remember, and if we get into trouble, we can just do things differently the next time. But if you program a computer to solve these things automatically, which is what we're really doing, what we're really talking about, then your computer is not quite as smart as you, and it might not realize what's going on, and it's just using some rule for picking the entering variable and for picking the leaving variable, and it may unfortunately get into a cycle. And once it does that, it's an infinite loop, and the thing never finishes, and that's a bad thing. So, but there's ambiguity in the pivot rules. There's a choice of who I pick to enter if there's lots of things that are positive. And there's often even choice of which variable will leave. We didn't have any examples of that yet, but when I do all these little ratios, there could be 2 or 3 of them that were a tie on which one will leave. So you have to talk about rules of how to pick the leaving variable when there's ties as to which one hits 0 first. And so the simplex method, as I showed it to you, is not a well-defined algorithm. We have to specify what these particular rules are. So we call these pivot rules, and I've been advocating the largest coefficient rule, but we don't have to use that rule. It's just common thought. It makes the greatest rate of increase, but it might not make a big jump. Anyway, the hope is that if we use some smartly chosen pivot rule, such as the largest coefficient rule, we can prove that the simplex method will not cycle. So let's see if we can do that. Well, it turns out that, that the largest coefficient rule is not immune to cycling. And here's the smallest example known in the world, I believe. I could be wrong about that. But I just figured this one out a few weeks ago. It's hard to find these examples. And this is a minor modification of a well-known example, but it's a better one, I think, because the numbers are smaller. It's been proved 50 years ago or something that you cannot have cycling in a problem with less than 2 variables and 4 constraints. And by the way, I didn't need this extra, sorry, I said that backwards. 2 constraints and 4 variables. I didn't need this last constraint here. I only put this on because I wanted to have a problem where once that we can at some point make a non-degenerate pivot and move away from this area of cycling. So if I hadn't had this as a constraint, then there's nowhere to go. The objective function has to be 0. So I only threw that on just to make the cycling be taking place at a non-optimal point. You can cycle at an optimal point and just not realize it's optimal because you're cycling among all these degenerate representations of the problem and not ever discovering the one that tells you, oh, this is, by the way, optimal. So anyway, this is the smallest example. And let me show you what the pivot tool does. Did I say what the rules are? I had to be very specific about it. The entering variable is the largest coefficient rule. The leaving variable is what's called the smallest index rule. Index of the subscript, right? So 1 is smaller than 2, is smaller than 3, is smaller than 4. So x1 comes before x2, before x3, before x4, and the w's come after the x's. So w1 comes after x4, and w2 after w1, and so on. So we pick the smallest index when there's a choice in the leaving variable. So if we use that rule, x1 is the entering variable here, and the smallest index rule tells me to use w1 as my leaving variable, smaller index than w2. So I do that pivot, and I get to here. And so now 5 is bigger than 4, so x2 is my entering variable. And x1 comes before I'm putting the w's first, not the x's first, I guess. Oh, I forgot my ordering here. So W2, or maybe I typed this wrong. Anyway, what did I do? I used X1 and X, yes, I did use W2, yes. Okay, so the W's come before the X's. I forgot my convention. So then W2 goes here, and now I have X3, and I look here, and X1 comes before X2, so it's X1 and X3 swap, and here, anyway, you go through, and you just follow this rule rigorously, and you get to here where W1 and W2 are back on the left, and X1, X2, X3, and X4 are back on the right. You're back to the original dictionary. The columns have been swapped around a little bit, but that doesn't matter. It's the same dictionary. And so we're back to where we started, and we've cycled. So this phenomenon is very rare. I recently, just a month ago, wrote a program that generates random 2x4 problems that are degenerate, so both the right-hand sides were 0, and I ran this 1 billion times and did not find a single example that cycle. So it's hard to find. But I did find this example, but I didn't do it randomly. I took a known example from 40 years ago or something and started with it and just made small changes to it to try to make the numbers better. So this isn't that different from the well-known example. Okay. So degeneracy can be a problem because you can cycle. It's extraordinarily rare, at least on 2x4 problems. I don't know how rare it is on bigger problems. Probably not so rare on bigger problems. That are lots of degeneracy. So we need a method for addressing this. And the method that I want to show you is called the perturbation method. So here's what we do. We have a problem here that I'm showing here with just two variables, x1 and x2. And the right-hand side is 0, all zeros. But I'm going to perturb the right-hand side by adding epsilon 1. I didn't know how to make an epsilon in Java. So I'm going to put an epsilon 1 and add it to the first right-hand side. Epsilon 2 I'm going to add to the second right-hand side. And epsilon 3 I'm going to add to the third right-hand side. So I put this little identity matrix multiplying this epsilon 1, epsilon 2. This is now a new symbolic right-hand side. It's no longer all zeros. It's zeros perturbed by these epsilons. And these epsilons are not numbers. They're just symbols. And the symbols will have the following properties. Whenever I'm doing ratios, whenever I'm checking inequalities, the data for the problem will be big compared to the epsilon 1, which will be huge compared to epsilon 2, etc. But all the epsilons will be positive. So without giving them particular values, we think of them this way. So if I do that, and then I use the largest coefficient rule, so I pick the 4 to enter, and I go down here, and I have two choices here for the leaving row, the -1 here and -1 there. But W1 can go up to epsilon 1. I mean, x2 can go up to epsilon 1 before W1 hits 0. And x2 can go up to epsilon 2 before W2 hits 0. But epsilon 2 is way smaller than epsilon 1, so W2 hits 0 first. And so W2 is my leaving variable, and I do the pivot. Now I have a 14 here, and I think I showed it on the next slide. I have a 14 here. Now I look down, and I have the -2 and the -1 here. This x1 can go up at a rate of 2, has to go up to epsilon 1 minus epsilon 2. Epsilon 2 is tiny compared to epsilon 1, so that's basically epsilon 1. Whereas this one can go up to epsilon 2 plus epsilon 3, well, that's tiny, so basically epsilon 2. So, and that's at a rate 1, this is a rate 2, but that doesn't really matter. So the fact that this one can only go up to epsilon 2, and that's way smaller than epsilon 1, tells me that W3 must be the leaving variable. And so I do the pivot, and I've solved my problem. I didn't do it. So the important point here is that every iteration now, even though I'm doing degenerate pivots, my symbolic objective function is strictly increasing. Because with the epsilons in there, I never did a degenerate pivot. And furthermore, you'll never get a row with all the epsilons having coefficients of 0. Because all of our pivot operations are reversible, and this is an identity, we started with an identity matrix here. If you think of this little matrix here, this is a full rank matrix. It's not possible to do pivots and reduce the rank of this matrix. And so you'll always have some epsilons. You won't get a row of 0 coefficients in this little 3x3 matrix. You'll always have some epsilons. You'll always be doing non-degenerate pivots. The objective function, the right-hand side is never 0 with the epsilons. But they were just symbolic parameters, and so once you're done, once you've gotten either solved the problem, or once you've just gotten out of the degenerate situation, you can throw away the epsilons and say, I don't care about them, I've solved my original problem. So the perturbation method is a very simple and useful technique for addressing the problem of cycling. There are other pivot rules that one can talk about. There's the smallest index rule, which is to choose the variable with the smallest index. So for entering variable, that has to be choose the variable with a positive coefficient that has the smallest index, rather than the largest coefficient. So if you pick both the entering and the leaving variable using the smallest index rule, that's known as Bland's rule. And Bland's rule has been proved not to cycle. You can also select at random. And that's a good thing, because then the probability that you may cycle, because you just selected things at random, but the next time you'll select things at random again, you'll make a different selection and you won't cycle. So random selection is also a good rule for avoiding cycling in practice on a computer. People have also considered the greatest increase rule, actually figure out which of the possible entering variables would give me the biggest increase in my objective function. But that actually, if you think about it, is doing a lot of numerical linear algebra per pivot, and the expense per pivot goes up quite a lot, and so that rule is actually not competitive computationally. Okay, just a brief few words about the geometry of degeneracy. So our inequalities, of course, are hyperplane, or half spaces, and we're intersecting these half spaces in n-dimensional space. And so our feasible set is, in 2 dimensions, is a polygon, and in higher dimensions, it's a polytope, multifaceted convex object. The simplex method is going from vertex to vertex. So we start, say, at 0, 0, 0, and when we increase just one variable at a time, say if I picked x1 as my first entering variable, a dictionary corresponds to a vertex, basically. And so if I did the first pivot with x1 entering, I would pivot to here. If I did the second pivot with, say, x2 being my entering variable, I would go to this vertex. If I picked my next pivot with x3 as my entering variable, I would go to this vertex, and so on. And you'll notice each vertex here has this vertex is the intersection of 3 planes, and knowing which of the 3 planes determines that vertex also determines which variables are the 3 basic variables for that problem. Those are the actually it tells me which variables are 0, so it tells me which ones are the non-basics. Anyway, look at this corner up here. Look at this example. In this example, the corner up here actually has 4 faces defining it. There's the 3 colored ones, but then there's the back plane, the x2, x3 plane. So there's 4 faces making this single vertex, but a vertex is defined by just 3, and so there's multiple ways of expressing this same geometric point. I have to pick 3 of the faces I said it wrong a minute ago. To determine my basic variables, those are the anyway, so I have multiple ways of representing this vertex here. I could say that x2, let's see, this point here, it has x2 equals 0, x1 equals 0. It has, this inequality has a 0 slack, so that's, is that the first or second one? That's the second one, so that's w2 is equal to 0 at this one, and w1 is equal to 0 at this one. So of those 4 things, I have to pick 3 of them to be non-basic and 1 of them to be basic. And so there's 4 different ways of doing that. And so there's 4 different dictionaries that represent that single geometric vertex. So that's what the degeneracy is geometrically. It's too many faces coming together at a single vertex. Okay. Now, another thing is, and probably the most important thing, is the efficiency of these algorithms. And the simplex method is a very efficient algorithm, and that's why after 60 years or 70 years, it's still very popular. So, given a problem of a certain size, how long does it take to solve it? How many iterations does it take? It's easy to figure out how much work per iteration, so the main question is how many iterations. And there's two kinds of answers, of course. There's the average performance on typical problems of a certain size, and there's the worst case performance on the hardest problem. The average case is, of course, mathematically difficult because you have to introduce some probability space and say what's an average problem. What's a random problem look like, and then try to take the average of how many pivots it takes. Very difficult. But it's easy to do empirical studies, and I'll show you one in just a minute. The worst case analysis is to say, well, let me try to construct a really bad example, make it the worst possible example. And that actually we can do, and I will do in a few minutes. But it turns out that for the simplex method, there's a huge, huge difference between the worst case and the average case. And so even though this is interesting, it's in practice of limited value. Okay. It's also, I think, useful to think about how one should even measure the size of a problem. I give you a matrix A, B, and C. That's the data for the problem. One could call the size of the problem M and N, but that's two parameters, not one. And size should just be one number somehow. So you could refer to the number of data elements, which is roughly M times N. It's actually M plus 1 times N plus 1 if I throw in the B and the C. And I have to subtract 1. Anyway. But real-world problems, the A matrix is usually extraordinarily sparse. Zeros all over the place. And so we store these matrices not as just dense two-dimensional arrays, but with sparse matrix technology. And it doesn't seem quite fair if I have, say, just a diagonal matrix, an n by n matrix, which is just all zeros and just numbers, except for numbers on the diagonal. Seems unfair to call that an n squared sized matrix data. It's just n. So it might make more sense to represent the size of the problem as the number of non-zero data elements. Or you could even say I have some language which allows me to formulate problems, and my favorite language is AMPLE for optimization. And how long is my little model that expresses the problem together with the data that goes with that model? How big is that? And that's really the size of the problem. Anyway, these things, it's a little bit tricky as to what you really mean, but people tend to just use the simplest things and stick with M and N, even though it's not really quite right. And also measuring time, of course, computers get faster all the time, and so the time per iteration is changing with technology, but the number of iterations is the fundamental mathematical thing, and so we focus on that. So here's the famous worst case problem discovered by Klee and Minty, published back in 1972. It looks like this. So it's got all these, the data is growing exponentially with powers of 2 and powers of 100, and it's a big mess. But if we look at just the n equals 3 example of it, here it is. And if we look at this, let's look at the constraints. The variables are non-negative. The first constraint just says that x1 is smaller than 1. So x1 is a small number. Well, it's between 0 and 1. If x1 is between 0 and 1, then 4x1 is between 0 and 4. And so roughly speaking, the second constraint is saying that x2, which is already known to be bigger than 0, is less than roughly 100. Not exactly 100, it depends a little bit on x1, but roughly 100, 96 to 100. And so x1 is between 0 and 1, x2 is between 0 and 100, x3, by the same kind of logic, that even though x1 and x2 appear here, they're kind of smallish numbers. And so roughly speaking, x3 is between 0 and 10,000. So this looks like a distorted cube, actually, and I have a picture of it here. It looks roughly like this. It's not exact. Of course, the things have been stretched. This is from 0 to 1 here. This is from 0 to 100 here. This is from 0 to 10,000 here. So it's not a cube in the sense of having the same size in each direction. But furthermore, it's not exactly a cube because the heights are not all the same. This is 9,992, 9,592, 9,600, this is 96, and so on. But it's almost a cube. And I should go back. If we do the simplex method with the largest coefficient rule, what was the largest coefficient? The largest coefficient is 4 on x1. So x1 wants to enter, but when x1 enters, we can only go this short distance to the 1 here. And once we've done that, we're sort of in trouble. And actually, here's what happens. We go from here to here, to here, to here. Now we go up to here, then we go over to here, over here, over here. We visit all 8 vertices, taking 7 pivots to do it. 2 to the n minus 1 pivots. And that's true not only with n equal to 3, but in all cases with the Clementi problem. I think it's fun and interesting to understand this fully. And the original Clementi paper is a little bit hard to read, I thought. And so I spent some time thinking about it and came up with, I think, a good way to understand the Clementi problem. And so, first of all, these numbers 1, 100, 10,000 are not terribly important. We really just want a sequence of numbers B1, B2, B3, and so on that are increasing very rapidly. But more importantly, at least for making the problem simple to understand, is not to just have the first right-hand side be B1 and B2 and B3 and B4, etc., but have B1, and for the second right-hand side, make it 2B1 plus B2. The third one should be 4B1 plus 2B2 plus B3, and so forth. Because B4 is huge compared to B3 and B2 and B1, this is still essentially the same number B4, but I've put these little pieces on here. This is like the perturbation method that I showed you a few minutes ago, in that these things don't matter very much, but they make a very simple pattern appear as we do the pivots, and that's the key here. So let's see, do I have this thing coming up? Oh. So here it is. Let's see if this is going to pop up for me, or shall I go to my, maybe I'll just go to the Clementi. Oops, hold on a second. I should exit this, kill this, go up here. Is it Cle underscore Minty? No, Clementi. Okay, what size? Should we do 4 by 4? Okay, here we go. Here it is. So all of this stuff here is just my objective, my parameterized, whatever you want to call it, modified right-hand sides. The actual variables are here. You got your geometric progression on the coefficients here. You've got zeros on the above the diagonal. You got ones on the diagonal. You've got this geometric progression below the diagonal, which, by the way, skips the number 2, and I've actually never understood why. And I suspect you don't need to do that, but I'm not 100% sure. Interesting, simple, maybe, minor research question. Could I have done this with 1, 2, 4, 8 instead of 1, 4, 8, 16? Not sure. I just stuck with what Cle and Minty did originally. But I did discover that over here, 1, 2, 4, 8 works. And that's why I suspect it works over here as well. Okay, so here we're going to do the pivots. 8 is the largest coefficient, so 8 must enter. If 8 enters, who leaves? Well, let's see. W1 can only go up to 1, because all these other, only up to B1, I mean. All these other coefficients are 0. So we always have 0 above the diagonal here. And so I have to pick x1. And so I did that pivot. And now I see the largest coefficient is 4. And there's a 0 here. There's always going to be zeros above the diagonal here. And so I have to pick one of these. And it turns out that W2 basically is of the size B2, and W3 is basically the size B3, because we always have zeros above here. And so B2 is much smaller than B3, is much smaller than B4, so W2 is going to be the one to pick next. So X2 goes with W2. By the way, you can think about it. Whenever I pick something, the entering variable and the leaving variable are in the same position. So if it's the first one there, it's the first one there. If it's the second one, and so forth. So I'm always clicking on these diagonal buttons, actually. But anyway, I did that second pivot, and now this 8 pops back in here, so I have to click on this button again. And now I've gotten both of those all right, but now there's this 2 here, so I have to click on this button. But when I click on that button, it brings that 8 and the 4 back. So you can see that this is kind of bad. So now I have to click on here, and then I have to click on here, but that brings the 8 back. Then I have to click on here. Okay, I'm half done. Now when I click on here, brings all the 8, 4, and 2 back. I have to click on the 8 again. By the way, we're counting to 2 to the n in base 2. That's exactly what's happening there. I can write that here. If I do this in reverse order, left, we put this on the, I'm going to put a 0 or a 1 associated whether this is purple or not. I'm going to put a 0, 1 whether this is purple or not, whether this is purple or not, and so on. 0 for purple and 1 for not purple. So they were all purple originally. And I'm putting the W1 here and the W4 here. And after the first pivot, I made this one good, but these guys were bad. After the second pivot, this one became good, but that one went bad again, and these were still bad. After the next pivot, I fixed this again. This was still good, and these were bad. After the next pivot, I fixed this one, but then these went bad. After the next pivot, I refixed the W1 one, and so on. So you can see clearly that I'm just counting to 2 to the n in base 2. There's even more nice properties here. I don't know if you've noticed them. Anybody notice any other nice properties that I haven't mentioned? Should I do another pivot? If you have a property in mind, check it. I'll pivot on this one, see what happens. I claim that the dictionary is very easy to predict. Can you predict what the next, every element of the dictionary is easy to predict. If I click on this, can you tell me what happens to all of the numbers? I already told you that the super diagonals, above the diagonals, stay 0 all the time, but that's not all that happens, a lot more than that. You see what happens? Anybody see the pattern? All the numbers stay the same, except for minus signs. The only thing that changes are minus signs. And I think what happens when I click on, I don't remember off the top of my head exactly what the rule is, but when I click on this, I think I negate the row, I negate the column, and this gets negated twice, and so that stays the same, I think. In fact, I think I forget exactly. I forget what happens to these. Do those change sign? Let's just click on this guy. Yeah. So I forget exactly what the rule is. But it's a very simple rule. So anyway, we're just counting to 2 to the n base 2. Yes?
Is it possible to increase the font size a little bit? Because
Oh, I'm sorry. Yes, I might have that. Oh, maybe I don't. Giganti big font, okay. Oh wait, 4 is not a good number. That's going to be too big. Is that better? Sorry about that. Okay. So let me do it again. So we pick the x1 here, and you see that the numbers stay the same. It's just the minus signs change. So if we look, for example, at this column here, it's 4148, and it's going to stay 4148. It's just who has the minus sign changes. Oops, now I have to go here. Now I have to go here. Now I have to go here. And there's also a very simple rule for exactly how the signs change. I just don't remember it off the top of my head. So that's it. Okay, it's been an hour, so maybe we should take a 5-minute break.